derivation of quadratic relations from higher topological quantum mechanics in general. And Morse theory as an example. So the goal is not to explain Morse theory. The goal is to show the power of higher topological quantum mechanics. So we will start with higher topological quantum mechanics, where we have V, space of states, Q, differential, G, so-called unnormalized homotopy, H, anticommutator of Q and G, we will use observables. At the moment, they are phi I operators. And we demand that Q phi I commutator is closed. So setup is very general. And what we are going to study? We are going to study correlators as differential forms on and here let me put it R plus to the power k defined as. But before I say how I am going to define correlators, I need to introduce one more concept. And this is a concept of vacuum. Sorry. I have an evolution operator. And let me assume that, so it's UT, that there is a limit it is easily to check. that if such a limit exists, it is a projector. Actually, okay? So what is the space on which we project? On kernel of H. So I assume states HA such that in what follow, okay, so these are vacuum states. By definition. Now, since QH equal to 0, space of vacuum states form a subcomplex. In the complex V. Now I'm ready to define the correlators that I'm going to study. HA phi 1. And here is my favorite exponential. T1H plus DT1G. Phi 2. Exponential. T2H plus DT2G. So here I'll have phi k plus 1. And here I have HB. So it will be the main object of study. So what can I say about this object?
I'm sorry. Do you use H to denote the projection?
Yes, I know. I use it like this. So this is a dual.
All right.
So this belongs to differential forms on RK, taking values in endomorphisms of the space VEC. Now, I will do the following. So I have to define this somehow. Let me call it I. I am going to study integrals of I over R plus K and find quadratic relations. I will use here two facts about I. First fact is factorization. What factorization means? Let say T2 go to infinity. Then E2 T2H goes to projection. So it means that I symbolically write like this. And here I have something, say T2 goes into I. This and this. And here I have composition in endomorphisms of vacuum. Second statement that I'm going to use. It's called relative closeness. Closedness. What do I mean by this? I is a differential form. So what can I do? I can compute di. So this d, I put here t. dt is a differential with respect to all ti's. I want to go from easy to hard. Easy case. Assume that Q acts by zero on VAC. Okay? then closedness follows from basic property of higher topological quantum mechanics. That is D plus U I will write it again. It's an important thing. It should be written several times. Equals Q. I would even write it as a commutator. So, what would happen if I apply D to I? I would apply this D to all exponentials. When I apply D to all exponentials, due to the main property, I can replace it by Q commutator. And Q commutators would act where? They would act on phi, but phi are Q closed by definition. And they can also act on H's. But I'm working in the easy case. So in the easy case, di is 0. Tim, is it clear?
So, and here again, dt is different from Q.
dt has nothing to do with Q. That's why I write it by different letters. But the main property of topological quantum mechanics intertwines dt with Q.
Yeah, all right.
So it was an easy case. Now, hard case. Not that hard. dti equals qi. Here, I belongs to endomorphisms of VAC, and Q are acting on VAC. Okay? So even the hard case is not that hard. Now, how can I compute interesting relations? I take I and I integrate I over the boundary of configuration space. Now, this would be 0 in the easy case. It would be Q applied to I in the hard. Now, what is interesting about boundary of configuration space? We may use factorization. So I, schematically, I restricted to the boundary is symbolically I times I. So this is the origin of quadratic relations. So let us, so I restricted to the boundary goes like this. And here we study integral. So integral goes into composition of the integrals. So in order to understand it, let us study it case by case. So first we will study easy case. Only one phi 1 standing here. No t's. Not that interesting. Configuration space is the point, and integral of I over the point is what I would call let me call it like this, n a b, and here I will have phi 1. Now suppose I have phi 1 and phi 2. And I have T standing here, and here I have A, and here I have B. Configuration space is formed by two copies of R plus. We have this situation, and we have this situation. Note that I want to have only T going to plus infinity boundary, where I have factorization. However, R plus has two boundaries. So this is R plus. You may ask, what about boundary T going to 0? So here I need to say that I forgot to add extra condition. It's my mistake in presentation. Phi I, phi j. I forgot. It was not. It's my mistake in explanation. Under this extra condition, contribution of T going to 0 boundary cancel between two copies of R plus. Why I kept this in mind?
I'm sorry, it's not clear. So this R plus, it is, well, it's topologically the same as R plus, but originally it doesn't really look like this, since we have 2 points and they're ordered, so the configuration space looks more like R times R plus, or
So
something of the sort.
let us study. Suppose we have ordered points. Then configuration space is actually R plus. You see, I wrote here this line. It corresponds to the vacuum state. So the only parameter here is T that stands here. And I want to add together two copies of R plus. And also here is T. So I have two copies of R plus. So actually, boundary of the first R plus is 0 and infinity. Boundary of the second R plus is also 0 and infinity.
Yeah, now I get it. Yeah, I just misunderstood the words two copies.
So here I want to make remark. Remark is something that is good for understanding, but not necessary. Not necessary. Origin of condition phi1, phi2, commutator, or graded commutator equal to 0. From the deformation theory, we observe of QFT that Q was deformed. So it is a remark. Condition phi I, phi j equal to 0 correspond to Q deformed squares to 0. But this is a remark. That's why I want to demand this condition. And it will be true in examples. Okay. So I am continuing with the easy case.
Oh, and just to be sure, and the phi's are Q closed.
Yes, phi's are Q closed.
Okay.
Now, how the story goes. Now I have R, not R plus. Of I is 0. However, this is the following. Phi1, phi2, infinite distance. phi 2, phi 1, infinite distance. Now I use factorization. So it is actually a point. And this is actually a point. So using factorization, it is integral of I phi 2 composition integral of I phi 1 plus, so actual sign would be minus.
Perhaps we should add some notation to I because
We
but they actually have
so
different.
there was a notation for I.
No, I mean I has different fields inside, and we use the same letter.
Okay, I get it. So it is I phi 2 phi 1. Okay,
Yeah, I guess.
and here the picture is like this. Okay, so relative sign is minus here. I phi 1 phi 2. And here I use factorization. And if you wish, I can put here AB, and I also put here AB. And here I use factorization. And then I get, sorry, I see phi 1, I see B phi 2. And here, all the way around. And this is the first quadratic relation. I called. So I was a function, and n is its integral. Okay, so when we can do this case, we can do more complicated case. phi 1, phi 2, phi 3, A, B. So now configuration space is R squared made out of 6 R plus squares. The way to draw it is like that. We have 6 cones. Each cone corresponds to some ordering of phi I. On these lines, points coincide. Coincide. It's kind of a standard picture. Now, there are boundaries. And it is easy to draw these boundaries. It's typical boundary configuration. Let us see what happens if we have this boundary configuration. Sorry. Now we take integral of our boundary component. Would be called NBC by 3, 5. Because this integral comes from phi 1, phi 2, phi 3. So altogether we have relation. That looks like so if I combine everything together, plus all permutations of phi i's. Because all permutations of phi i's correspond to all boundaries.
Wait, but not all permutations. Like,
All.
we shouldn't include phi 2, phi 1, phi 3 because we already included it in the definition of n. Isn't that right?
You see, when I wrote it like this, okay, so actually I made a mistake here. Plus, there was a component of the boundary that I made. plus all permutations. Because the second term was actually coming from the configuration phi 1, infinitely long distance, phi 2, phi 3. And this sum equals to 0.
Can we return to the definition of n? And what's it? What's the point? What is the meaning
Okay.
of this n?
So n is the integral of I phi 1 phi k. Okay. And phi 1 is the integral of I phi 1 phi k over r rk minus 1. That is the integral of I. And here I have non-ordered. So in the definition of n, I integrate I over the full space. So this was the definition of I over ordered set of observables. Let me put it like this. And here I sum over all permutations. So it is integral of I over an ordered set of observables. And here, I'm sorry, k minus 1 should be here. Like n phi 1 phi 2 is integral over r of I phi1, phi2. That is integral over R plus I phi1, phi2 plus integral over R plus I phi2, phi1.
I think there's something wrong with the line above. So
Here,
yeah, this one. So r k to r to the k minus 1, it has like what, 2 to the power k minus 1 connected components, since we
no, it has not it has not 2 to the power k minus 1. It has k minus 1 factorial.
yeah, that's what we would like to have, since we have a sum, but on the left hand
Okay,
side,
let me check. Let me check this and this and this. So here I have sigma k. I'm sorry. So here it's still sigma k. And here is an example for k equals to 2. And here is an example for k equals to 3. So there is k factorial ways to distribute point in order. Probably I can illustrate this in the following example. Consider the space R to the power k. And take a quotient over R. And let me call this space config. So how I am taking this quotient? I take the set of numbers T1, Tk, and I identify T1 plus, I need another letter, T, etc. Tk plus T identified with T1, Tk. It is clear that this space is R k minus 1. At the same time, if all Ti's are different, I can order them, right? And the same space config may be given like this. Consider the smallest point. Then point next to smallest. And so on. With Ti being strictly positive. So you get k factorial configuration each isomorphic to R plus to the power k minus 1.
I get it now. I was partitioning this space into wrong pieces. Now it's clear.
Okay. Now we need to make a break. So let me continue. So what I am going to say? I am going to say that in the easy case, these quadratic relations may be written as follows. Define universal observable. Phi. That is the sum of phi I, tau I. Such that parity of phi I plus parity of tau I is 1 modulo 2. Defined universal relation. NAB of tau the sum over k, 1 over k factorial, NAB phi of tau, phi of tau, k times then relations take the form NAB NBC square to 0. So it's a combinatorial state. Now let us return to hard key. When Q on VEC is not 0. Inspect our derivation. Now it's not 0. However, we know what it is. It is Q applied to I. Again, integrated on the same space. So on the left-hand side, we see the boundary of derivation. On the right-hand side, we see the bulk. But we are not afraid, because it's Q, and here we will have this N. Remember that here we had this. Okay, I need to be more explicit. I went too far. Here we had di. Now di is not 0. And we have the right-hand side, where we have QAC ICB integrated on configuration minus IAC, again integrated on the space of configurations, and here we have QCB. Here QAB is the action of Q on the vacuum subspace. But we are not afraid, because we understand that these things would combine in the same objects like n. Altogether, we have an equation NAB of tau NBC of tau equals UN AC. This equation again has a nice meaning. It says that QAB plus NAB of tau squares to 0. So up to now, I was studying very general case. It was abstract. Then I want to study Morse theory. As an example, remember that we had V being differential forms on manifold X. And we had H that was LV. So the question was, what is vacuum? And there is a notion. Is omega epsilon that I introduced before. And here is the concept of Lefschetz symbol. A. What is the Lefschetz symbol? You take a critical point you consider all trajectory coming out of this point. So one picture is more important than many formulas. Consider an example. So it's a hard figure. And W grows down. So there are critical points. A, B, C, D. And there is a trajectory going like this, and trajectory going like this. There is a trajectory going from A to C. A trajectory going from B to C. Blue figure is LTA. A red figure is LTB. Okay? Union of two trajectories coming out of C is left symbol of C. And point D is the left symbol of D. So one thing is clear. Left symbols are invariant with respect to LV. It's obvious. If I have a point on the symbol, and if I start a flow, I will still be on a symbol. Second, differential dx. You see, I put here x in order not to mix it with t. Turns left symbols into left symbols. In the picture, what is d applied to omega LTA? Let me put here epsilon. We spent some time trying to understand differential forms associated to figures. We will use it. It is, of course, omega, epsilon. Here we have derivative of Lipschitz symbols A. And it is clear that this is omega epsilon, and here we have Lipschitz symbol C. So it works. Okay. Now I want to make one more picture above this picture. So how to see that limit when t is going to infinity of e to the t lv applied to differential form is one of is a sum of I will write it as a formula. By inspection. Take a curve that go like this and like this. Okay. So you may ask, where does it flow? So let me call it gamma. Where omega gamma flows under the LV flow. I will use that e to the t LV omega of z e to the t LVZ. So differential form that is concentrated on a side or on a chain flows with the chain. So here I have this line. So where does it flow? This point flows to D. I'm sorry. Алло? Я сейчас занят. So it goes to the opposite side. So this point moves here, while the opposite point moves to the same point D. The middle point moves to C. So on this figure, we see that omega of gamma flows to omega LTC.
I have a feeling that there should be a different sign in this in the previous formula. Am I wrong?
Flow is flow.
Yeah, but I mean, we can either first integrate with omega and then act with the flow, or act with the inverse flow and then integrate with omega. Isn't it like this?
Maybe you are right. I need to think. But I think that the flow, but I think that the direction is correct. The direction that I show is correct. That when you flow such differential form, it flows in the proper direction. So duality was already made in the, it's called Poincare duality, in writing differential form that corresponds to the figure. But you see, I drew you the picture. And that's why you may study several questions. And the first question is, how to compute the number of curves going through points. and I'll redraw it. And I have only one trajectory going from A to D. Through the point E. Now I can ask a different question. Another enumerative question. What would happen if I move a point E to E prime? There is one trajectory here, but if I move a point to E prime, no trajectory. And the question is, what is the reason for it? The reason is still in the main formula. We studied integrals of phi1, phi k. We may ask, what happens if phi I goes from phi I plus u of phi tilde I? Geometrically, it was the following question. Phi I was omega in this case phi, was omega associated to the point E. So phi tilde was omega associated to the interval E tilde. Q was just the RAM on X. So we may ask what happens if I do such transformation. Since VEC is not Q invariant, we have the following. Q of phi tilde HB is not zero. Actually, it is HB phi tilde UHA. But now we know that QH A is actually HC. So we have this point. And this is HB phi tilde HC.
I'm sorry, why is there no Q phi term, only phi Q on the
Because
commutation?
we are studying the difference. We are shifting. So we are studying the following thing. I should write it somewhere here.
You just say that the commutator is not zero. And
We study. 1 second. Okay. Maybe I should draw it a bit different, a bit more explicit. I call it phi E minus phi E prime. How do I compute it? Sage B, this is Q phi E prime. Now I take Q out of it and hit on HA. Now this is HB phi E prime QHA. So QHB equals to 0. I call it A. I call it HD. To be consistent with the picture. So this was the number of trajectories coming out of A, passing through the point E and hitting at D. This was the number of trajectories coming out of A, passing through E prime and hitting at D. So their difference is not zero. So naively, how I can argue that it is zero? I can replace difference between phi E and phi E prime by phi associated with an interval. Now I take Q out of it and hit to HA. Well, this is phi E prime, and here is HC. And this again has a numerative meaning. It's the number of curves coming out of C and intersecting the interval E prime. So if we go to the picture, we see that it exactly works like this. If E and E prime are on the same half, nothing changes. However, when E and E prime are in the opposite halves, there is a trajectory C to D that crosses this interval, and it leads to the change of the result. So what I showed you right now, it was just an illustration how things are working in Morse theory. In particular, we can use not only moral, we may use not only closed phis, but also non-closed. And still get relation between enumerative number. Okay. So that's all for today. And we will continue next Thursday. So questions, please.
I have a question about this path connecting E and E prime in this last example. It passes from this Lefschetz thimble A to Lefschetz thimble B, but it passes through this weird region, LTC, where there are like a lot of trajectories concentrated near this. Are there any problems? Is it a point of interest, or is it just a regular?
So when we look for the difference, we are looking only for the boundary of LTA. And the boundary of LTA is LTC.
Yeah, but we can. Isn't that difference of the boundaries kind of like the integral over the path of d of
So here I try to write down things both abstractly and geometrically. In abstract setting, we are changing phi e to phi e prime. And see that phi e and phi prime belong to the same cohomology class of the manifold. But they are just different representatives. And we are looking if the answer, this enumerative answer that are numbers, depends on it. And we work out abstractly. We change phi e to the phi e prime. We compute the difference, and we found that the difference is exact. So would Q act by zero on vector, the result would not change. However, Q was acting non-trivial on vector, and we may see this phenomenon. Taking Q out of phi e prime to the vector. So that's what I wrote in this formula. And we already know that Q on HA is HC. So this is kind of a prediction that the change of intersection numbers is again an intersection number, however, of the different kind. It is an intersection number corresponding to the trajectory coming out of C and intersecting the interval. And we see on the picture that it actually works. So here was algebra. And here is geometry. In algebra, you are manipulating with formulas. In geometry, you see how it goes. That whenever E prime is not intersecting trajectory is coming out of C. Nothing changes. However, when it intersects, you have a jump. So I think that that's why theories of Morse type are that interesting. You might read them both algebraically and geometrically. If you just write down the formula, you cannot see how it's working. You are just writing down formula. If you have two things together, formula and geometrical picture, you may see how formula works. So you may think with two sides of your brain, geometrically and algebraically. And the great advantage of mathematics is that algebraic description of mathematics and geometric description of mathematics are the same. In low dimensions, you can see what's going on. In higher dimensions, you can only compute. So in Morse theory, you have not only formulas and existence theorems, you also have pictures. Okay,